we have a mass of 100 kilograms accelerating at 40 centimeters per second squared, then we immediately conclude that the net force on that mass is the product of mass and acceleration, which is 100 grams multiplied by 40 centimeters per second squared, which is, of course, then 4,000 grams times centimeters per second squared. And people in the current class are doing quite well with the units and with the idea of calculating and writing down the units. It's very important. Now, you were given the information that a gram accelerating at a centimeter per second requires 1 dyne of force. It doesn't take too much to reason from that we would probably expect that 4,000 gram times centimeters per second squared would be 4,000 dynes. Okay, and that would be the force that would, that would be the expression or the name of the unit, gram centimeter per second squared. Okay, there's a little more to that reasoning, but we'll leave it at that for now, because people did make that conjecture, and that was correct. Okay. Alternatively, we could write that as net force is 100 grams multiplied by 1 kilogram per 1,000 grams multiplied by 40 times 0.01 meter per second squared. How can we do that? Well, multiplying by 1 kilogram over 1,000 grams, and of course we know that if we know what kilo means, we know that a kilogram is 1,000 grams. Multiplying by this is multiplying by the ratio of two identical quantities. 1 kilogram is the same as 1,000 grams, so this quantity is essentially just 1. And we multiply that by 100 grams, and the units come out grams times kilograms over grams, which is just kilograms. So we get 100 over 1,000, or 0.1 kilograms. Okay, now this is the same object, okay, so it's the 100 grams can now be expressed as 0.1 kilograms, and that's really pretty obvious. Probably don't need to explain that a whole lot. Okay, now the acceleration is 40 centimeters per second squared. Okay, I simply replaced the centimeter in the 40 centimeters per second squared by the equivalent measure in meters, which is 0.01 meters. A centimeter is 1/100th of a meter, since a meter is 100 centimeters. So I just replaced centimeter with 0.01 meter. That works just as well as doing this conversion factor thing, although it doesn't necessarily document and keep track of the conversion process quite as well. Still legitimate in a wide variety of situations. Okay, so this, of course, multiplies out to 0.4 meters per second squared. Then if we multiply 0.1 kilogram by 4.4 meters per second squared, we get 0.04 kilogram meters per second squared. And then, given the information that the force required to accelerate 1 kilogram at 1 meter per second squared is a Newton, from which we conclude that a kilogram meter per second squared is apparently a Newton, then if everything remains linear as it does, we expect that that's going to be 0.04 newtons. And that's the correct expectation. Okay? Now, let's emphasize that this F net equals mass times acceleration is expressing the fact that the net force, the sum of all forces acting on this mass, gives you this acceleration. Okay? That F net is the force, sum of all forces acting on the mass, and if you multiply mass times acceleration, that's what you get. It doesn't tell you anything directly about some of the individual forces that might add up to F net, and we're going to address that a little bit in the next question, but it does give you the net force, the sum of all forces. So for example, if you knew all the forces but one, and you knew the mass and the acceleration, you'd be able to find the net force, which would be the sum of all those forces, and then solve for the one you don't know. Okay? And you really want that perspective. You really want to write these things out very carefully from the beginning, so you don't lapse into a lot of erroneous reasoning and begin relying on that reasoning. You want to be very rigorous with yourself in the way you write these things out.